All right, so this video is going to be all about polar bonds and molecules. All right, because like it says, not all atoms are great at sharing. So even when you have covalent bonds, some of them are not going to share their electrons equally, and so you end up with something that is called a polar bond. But before we even get into polar bonds, what am I talking about by being polar? I think the best way to begin looking at this is looking at magnets, right? Because we're all familiar with magnets and hopefully familiar with the fact that magnets have poles, right? We tend to name magnets poles by north or south, though we can also think about them kind of as positive and negative. And essentially what these pictures here are showing is the magnetic field lines in some iron filings. This is kind of cool if you get the chance to do this in a physics lab or something someday. This is a kind of an interesting experiment. It's or kind of little demo. It's interesting to see that like you can actually physically see these magnetic field lines. But thinking about this, right, magnets, we know that the magnets are attracted to each other, right, north to south, and repel each other, north to north or south to south. You can kind of see in these pictures the filings, right, they flow between the two poles on the north and south, and there's this big space where the poles or the fields are pushing against each other on the north. And so when we say polar, right, what I'm really talking about is a division of charge. And so if we look, right, there's a division of charge on these magnets. One has a north and one has a south, or one has positive, one has negative. And that's going to be the same with polar bonds, right? And really what happens in a polar bond, it's that two atoms are differing enough in electronegativity that they are not sharing the electrons equally, and that this means the electrons spend more time closer to one atom than the other. All right, so like in this picture here, we've got a polar covalent bond between fluorine and hydrogen, and essentially fluorine, right, over on this side has most of the electrons here. We usually represent electron-rich areas in red, electron poor or electron deficient regions in blue, and then in the middle, right, electron neutral is generally the color green in any kind of diagram that you're going to see, and that's the general color scheme for any electron diagram that you're going to see. But essentially what happens is, because most of the electron cloud, or all this stuff here, right, the electron cloud is being pulled over to the side of fluorine, you're going to end up with one side that is partially positive. And how we show that is we write this lowercase delta with the positive. It does kind of look like a musical note, I've been told. I would kind of agree. That's a lowercase delta. All right, so a partial positive on this side, right, and a partial negative on this side. And why we say that they're partial is because, right, the electrons have not been pulled off of hydrogen, right? They're still sharing them. Got this big bubble here. They're still sharing the electrons, but fluorine is pulling on them enough that the electrons spend most of their time closer to fluorine. And so this makes something polar, right? Partial positive, partial negative, which means that there are essentially a charge on this molecule, right? Even though the charges in the molecule are balanced, right? You have positive and negative in the same molecule. There is still a separation of charge, and that means that polar molecules and polar bonds like this can actually interact with other polar bonds and polar molecules in ways that non-polar cannot, which we'll talk about later when we talk about intermolecular forces. So there is a slight difference between a polar molecule and a polar bond. Polar molecules, right, they're similar to polar covalent bonds in that they have their electrons distributed unequally across the molecule. And in this case, it also means that the electrons spend more time on one side, but this time one side of the molecule than on the other. Right? So if we take a look here at water, right, we've got these electrons that are actually going to spend their time up here. All right, plus the fact that oxygen is much more electronegative than hydrogen, so it's pulling those electrons up towards itself, which gives you that partial positive, partial negative, right? There's the delta plus, delta minus there. And if you look at the diagram down here, right, just like I had said before, red means a lot of electrons, blue means not too many. And so you see that overall this molecule has one side of the entire molecule that has a partial negative charge, right, a lot of electron density, one side that has partial positive charges, not a lot of electron density. So that makes it polar because it has a separation of charge. It's like the poles on a magnet. Now here, right, carbon and hydrogen don't have a large electronegativity difference, so there's not a lot of pull from the hydrogen to the carbon. And also, if you look at this, right, this molecule, and we'll get into talking about this later, is symmetrical in that it's the same on all sides, it's a symmetrical shape, and so there's not a whole bunch of electrons hanging out on one side or the other. And so we represent this all over as kind of neutral electron density. So the electrons are not spending any more time in one place than another. And like it says over here, right, polar molecules tend to have strong interactions, high melting points, well, high compared to nonpolar, and boiling points. And then nonpolar molecules, right, weaker interactions, lower melting points and boiling points. But we will talk more about that when we talk intermolecular forces. So here's something that I want to make clear when we're talking about polar bonds and polar molecules. Just because something has polar bonds in it does not mean that it is going to be a polar molecule. All right, if we look here, and I know this is kind of blurry, but I'll give you the rundown of what's going on here. We have carbon and oxygen, right? This is carbon dioxide. We've got carbon and oxygen. Oxygen electronegative enough that it is going to form a polar bond with carbon, right? It's going to pull electrons towards itself, and we'll get into this, but it's also got these electrons that are not bonded out here on the edge, right, of each oxygen, meaning that there's a whole bunch of electrons kind of hanging out here on the edge of the oxygen, which means that on each side of this molecule, right, there's a whole bunch of electrons hanging out, and that in the center, carbon doesn't have a high electron density. But because this is equal here on both sides, you've got oxygen on both sides, they're pulling equally in opposite directions, right? This molecule is not polar despite the fact that it does have two polar covalent bonds in it. Whereas here, right, with oxygen, because we've got these electrons hanging out over here and it's pulling electron density from the hydrogens, we do have high electron density on one side, low electron density on the other. So this one has both polar bonds and is a polar molecule, right? Water, polar bonds and polar molecule. CO2, polar bonds, but a non-polar molecule. And it all has to do with shape and symmetry, which we will talk about in a shape and symmetry video. So you might be asking, why does this even matter? Why am I spending this much time talking about polar bonds and polar molecules? Well, this is because I also want to talk about the like dissolves like rule and exactly how people use this in chemistry. So before we go further, some terms to know, solvent and solute. Perhaps you have heard these by this point in your high school career, but I will just review them here. The solvent is the substance in a solution that does the dissolving. It is always in the higher amount. And the solute is the substance in a solution that is being dissolved. So the rule: polar substances are more easily dissolved in polar solvents, and non-polar substances are more easily dissolved in non-polar solvents. All right, this is the like dissolves like. So polar solvents dissolve polar solutes better. Non-polar solvents dissolve non-polar solutes better. Like dissolves like. So this property, right, is often used to separate components of a mixture. In organic chemistry, you can purify or isolate desired products after a chemical reaction. Another example is styrofoam cups, right? You can set that on your counter with water in it for years, or it'll sit in a landfill for decades, right, without it dissolving. But as soon as you drop that in a non-polar solvent, something like acetone, right, that thing dissolves within seconds. I mean, it just basically disappears. So the like dissolves like rule at work. Like I was saying, in a chemical lab, chromatography. This is two types of chromatography here. On the left here, we've got what's called column chromatography, and this is what organic chemists will use to purify and isolate or separate what they want here. Like, let's say, you're running this through, and you know that you want whatever this stuff is, this black band here. So you can continue running solvent through this until, right, this is coming out, and you just collect all the solvent that has what you want in it, and then boil off your solvent, and you've got the product that you want, and not all the other crud. The other way that this is often used is in pictures like this, what we call thin layer chromatography, or TLC. Basically, you can monitor when a reaction is done, right? You have your starting material, your reaction, and your desired product. And so you just put spots of all of them. You put it in a little pan of solvent, so there would be like liquid down here. And as the liquid moves up the plate, that was a really bad arrow, right, it's going to move this stuff with it. And so at the beginning, right, you can compare. You've got starting material, and in your reaction, and then here's the spot that your product makes. And then at the end of the reaction, right, look, your reaction has moved up. So you know that you've made the product you want. You've got basically none of your starting material left, and so you know that your reaction is done. So this is a really good way to monitor how far a chemical reaction has gone and when it's ready to then purify. Right? The other way is with thin layer chromatography. Again, TLC, we can kind of separate some things to get an idea of what might be in there, to see if our product is even in there in the first place, and give us a kind of good idea of what's going on. And so this is some ways that in the lab, right, chemists actually use the like dissolves like rule and play around with the polarity to separate things out and make it easier for them to recover what they have actually made and are looking for. So to wrap this up, some things to remember: that polar means a separation of charge, right? Think two poles like a magnet. Polar bonds are caused by differences in electronegativity between the atoms that they're bonded. Polar molecules are caused by shape, right? Polar bond does not mean that it is going to be a polar molecule necessarily, right? Polar bonds do not mean polar molecule necessarily. And then let's remember the like dissolves like rule, because it is definitely useful in chemistry and kind of in our daily lives too. So there we go. Thanks for watching. See you in class.